Okay, welcome to the webinar, everyone. The topic for today's presentation is off-grid battery and charge controller best practices. This is a joint webinar by Trojan Battery and Morningstar. We are recording this webinar, and you will receive an email tomorrow with a link to the recording. As you listen to the presentation, if you have any questions, please go ahead and type them into the chat box at the bottom of your GoToWebinar pane, and we will address them in the Q&A session at the end as time permits. If we can't get to your question online, we will respond to you by email to answer your question after the webinar. Let's go ahead to the next slide and introduce our two presenters. First up will be Tom Lauder from Trojan Battery, and then we will hear from Doug Grubbs from Morningstar. Both Tom and Doug are applications engineers with many years of experience in the solar industry. And before I hand off to Tom, I want to just share the agenda of topics that we will be covering. We're going to start with battery basics, the different types of batteries, flooded, AGM and Gel, and then Tom will share information about ideal off-grid applications. Doug will then present on solar charge controllers, including charge setting adjustments, remote monitoring, and data logging, and finally, an outdoor lighting system sizing example. After the summary, we'll go ahead and address your questions. So with that said, I'd like to hand off to Tom Lauder of Trojan Battery. Tom?
Good day, everyone. I am going to start off with a little bit about Trojan and then move into the battery maintenance and go on from there. So you can see for Trojan, we have been around for a little bit over 90 years, and that in 2009 we launched our renewable energy division to concentrate in this new and exciting area of battery and energy storage. Real quickly, what is Trojan's purpose? We are to provide clean, reliable energy storage solutions that enhance the way people live, work, and play around the world. And that's really what we are striving to do. So, best battery practices. If you want to optimize the use of your deep cycle batteries, they have to be maintained. And maintenance is multifaceted, but one of the main components is proper charging and discharging of the batteries. You have to have the inverter and controller to work in conjunction with the batteries, with the proper settings, making sure that they don't overcharge or undercharge or over-discharge your battery bank. And that's why you want to have those proper set points set up for the battery bank being used. And it's not a case of one set of set points works for every battery type or even battery size. So that's why you really have to get that information and know, what your expectations are for the batteries that you're using in your system. Got a little bit of delay here, so that's why there's a little bit of delay when I'm talking about things. So battery basics, connections, and maintenance. So on this slide here, you can see that there will be a chemistry final at the end of the webinar, so be prepared for that. Now, this is just really a breakdown of what actually happens inside the battery. If you look in the lower right-hand corner there, you may have seen this on YouTube or Vine or some other places where they put two different metals and a lemon or an orange or a potato. and they put the meter on there, and you get a voltage difference. And if you connect the two pieces of metal, you'll actually get a current. And that's just your basic battery. It's taking current from a high potential metal to a low potential metal. In a battery that you buy from Trojan, the battery is rechargeable. The lemon or the orange or the potato is not. So you have a charge cycle and a discharge cycle, and that's what gives you the different chemicals that you have inside the battery after both of those. So when you attach a load to the battery, what you're doing is you're pulling current out of that battery, you're pulling electricity out, and that chemical equation that we showed before is taking place. But what you would see as a battery user is that the voltage, if you put a meter on the battery, the voltage would gradually go down. So it would start at 6.3 or 6.4 or 12.8 or 52 volts, something in that nature. And then as you discharged it, the voltage would go down and would become less and less. At the same time, if you were to check the electrolyte that's inside that battery, you would notice that the density of that electrolyte also goes down. It will start around 1.275, 1.28, somewhere in that neighborhood, maybe a little bit higher if the battery is older. And then as it discharges, that specific gravity number comes down. So in both cases, you're starting from a high point and going to a low point when you're discharging the battery or you have a load put on the battery. When I go and charge that battery back up, now I'm putting electricity back into the battery. And when I'm doing that, that voltage that just came down is going to start to rise and start going back up to that 52 volts or so on a 48 volt system, or 12.8 or something on a 12 volt system. So that charges is going to take it from a low voltage back up to a higher voltage. At the same time that that's happening, that specific gravity of the liquid, the electrolyte that's inside the battery, it's going to start low and move itself back up to around 1.275, 1.28, somewhere around there. So that's the basic things that you would see in measuring batteries, or things that can be measured between the battery discharging and the battery charging. There are different kinds of batteries. We are going to talk today about lead-acid batteries. There are two different types of lead-acid battery. There's a flooded battery that has electrolyte acid that is around the plates. It sloshes around. You can take the top off and look down and see the liquid level inside the battery. And there is what's called non-spillable, VRLA, some people AGM, some people Gel. All of those names really go back to that VRLA, which stands for valve-regulated lead acid. So your AGM battery and your gel battery are still lead acid batteries. They've got lead and they've got acid in them. The only difference is the acid that's inside the battery. In the AGM battery, it's held in a sponge-like material, so it doesn't slosh around. You can't open up the battery to look inside to see the level, but if you could, you wouldn't see any standing acid in there because it's all soaked up in that sponge that's around the plates. In a gel battery, you'll see, if you could look inside, you would see a material that looks kind of really, really viscous. And I got some pictures later on to show you kind of what it looks like. But again, you wouldn't see liquid acid around them. So in that flooded, you've got two kinds, maintenance-free and maintenance. Maintenance-free, built with lead calcium. Deep cycle is not really what they're used for mainly. They're used a lot for starting batteries. A lot of your car starting batteries nowadays, you don't put water in them anymore. They're maintenance-free. They've got all the liquid they're ever going to need. And with the calcium being in there, they don't really lose water very much. So that's kind of where they fit into the world of batteries. On the other side, there's maintenance. That's what you would have if you bought a Trojan battery. It's a deep cycle. It's designed to be used as a deep cycle battery, to be discharged and recharged. You have to add water to the maintenance battery, and it is designed, again, for deep cycle usage. And I talked a little bit about the gel and the AGM. Both of them can be used for deep cycle, but again, you're not going to add any liquid to them. You can see from the pictures there that that shows the flooded with a vent on top that opens. That's so you can put the water in. The VRLA shows it closed, so you're not going to have adding water to that one. I spoke before about voltage and specific gravity kind of mirroring each other. They go up when you charge, they go down when you discharge. This particular table that you see can be found on our website. It's also in the user manuals that come with the batteries when you buy them. And this just gives you a rough relationship between the percent charge, the specific gravity, and then the voltage either of a 6-volt battery, an 8-volt battery, a 12-volt battery, and you can use that to calculate out to a 24-volt system or a 48-volt system to get what the expected voltage would be at a percent charge. One thing to keep in mind in this particular case is we give one number. For instance, 100% state of charge is 1.277. Manufacturing process has variation to it. So you may not get 1.277. You may get 1.270, 1.280. What you're really looking for is to differentiate between large differences in percentage of charge. So if you're looking to see if you're at 80% charge, well, then you're going to be down in that 1240 range in specific gravity, 1.240. If you're at 100%, you're going to be up around 1.275 or somewhere. So the numbers there are just representative of a calculation of what the percent charge is. Your results may be a little bit different, but you're really looking to see what that voltage, gravity, and percent charge look like together. The other thing that you need to keep in mind here is that gravity says open circuit voltage. I got to see if this thing will work or not. I don't know if you can see that or not, but this says open circuit voltage right here. And what that means is that that's the voltage with no load on the battery and it's not being charged. And it also has to have been off charge for about 6 to 8 hours, because once you have charged a battery, and remember we charge it and the voltage goes up, well, if I just turn the charger off and I measure the voltage right then, I'm going to get a higher voltage reading than if I waited 10 minutes. And I'll get a higher voltage reading after 10 minutes than I'd get after an hour. So that voltage really is going to have to come back down and settle into what this would be called our open circuit voltage. And that's just one thing to keep in mind when you are measuring voltages or writing them down or checking your batteries. You're going to get that open circuit voltage after a period of time okay. I am Oh, there we go. Sorry, I had a hiccup here trying to get to the next slide. That was my bad. For AGM and Gel, you cannot check the specific gravity because they're sealed. So all you can go on there is the voltage. And again, there is a relationship between the percent charge and the voltage. And again, you can use that to calculate out past 12 volts if you want to look at a 24 volt, 48 volt systems or higher. Now, when you're connecting batteries together, you can do a couple of different things. You can connect them in series, and when you do that, you're going to increase the voltage of the batteries, but your capacity is not going to increase. So in this example, if I take the negative of one battery and connect it to the positive of another battery, then I'm going to go from two 6-volt batteries to a 12-volt battery system, but my capacity is still going to be the same as it was for the single 6-volt. I've just increased or doubled the voltage. You can do the same thing if you had two 12 volts connected in that same way. You'd get a 24-volt system, but your capacity would be the same as whatever that 12-volt battery was. Next to that, you've got the parallel connection, and you can see there that the positive is connected to the positive, and the negative is connected to the negative. And in that particular case, now I still have a 6-volt system, but I've doubled my capacity. And again, it works no matter if I take two 12 volts and put them together. It'll still be a 12-volt system in parallel, but my capacity will get doubled. And then you can combine the two to what we call a series parallel connection. And this is basically what most of the renewable energy type of applications have at least some parts of this. And there you get both the increase in voltage and the increase in capacity. And you can see you've got positive to positive on one battery, negative to positive to give you the series part, and then the negative to negative at the bottom of the group, which gives you the parallel that increases that capacity. So one of the things that we suggest is that you put no more than 3 strings together in a series parallel connection. The reasoning for that is because charging the series parallel batteries is a little bit more challenging than if they're just in series or just in parallel. And if you get too many batteries or too many strings, you'll get an imbalance. There's several more cables connecting the batteries. Well, the cables give you some variation. You've got more batteries hooked together, so you get variation battery to battery. So you're just getting more and more variation. And when you do that and you go to charge those back, then you can actually end up with some batteries getting more charge than others just because of impedance and how much resistance there is. So 3 strings is what we recommend to be the maximum. In the example you see in front of you there, you can see that the connection of all the 12 volts together is giving you the 48 volts. So that's the connection here. And then my parallel connection here, positive to positive to positive, and negative to negative to negative, is what's going to give me my amp hour increase. So if I take all of this together, I've got 48 volts, and I've got 450 amp hours in this whole system. Another thing to look at is, oh, sorry, I made a mistake. I'm going to go back to that screen. My apologies. Is the way that you hook up the leads that go to your controller or to your inverter. If you were to come off the positive battery here and the negative of this battery, then you're going to get preferential action on these batteries as opposed to string 2 and string 3, both in discharge and recharge. So what you want to do is pick the opposite corner in your setup, or opposite string. If you had 2 strings, you'd want to take your negative and take it off of string number 2. So in doing that, you are keeping the strings from being preferentially used and preferentially overcharged when they get charged back up. So what do you want to do with your batteries? Well, you want to keep them clean and dry. You don't want to sit them out in the weather where they get wet. Check all the vent caps are properly on the battery. Check the connections are tight. A couple of times a year, go and just back off a little bit and retighten the bolts onto the batteries to make sure that they've not come loose. If they get loose, you can actually have a place where the terminal on the battery will melt, because that loose connection will cause a high resistance area and it'll actually heat up. It'll be kind of like a heater that you have that the coils get red in there because they have a high resistance, and that causes the terminal to melt. If you do happen to have any residue on top, you can clean that up with a little baking soda and water mixed together. Do not allow any of that cleaning solution to get inside the battery. So you want to keep the caps on while you're cleaning and rinse and get rid of it and dry it. Then if you want to take the caps off to do a visual check on the water level or something, but do not clean with the caps removed. And of course you can put a little terminal spray on the connectors to help keep them from corroding. Storage. Batteries should be charged before placing in storage. If you are at your hunting cabin or you're somewhere and you're going to go away for 6 months or something, then you want to make sure that you get your batteries charged up before you place them in storage. Again, cool, dry location. Disconnect equipment from the batteries. If you happen to leave them connected and you happen to have something that you don't think is really drawing much of a load, but you're going to be gone for a couple of months, it doesn't take many amps for a month or two to really draw down the capacity of the battery. So you want to make sure that you disconnect from any equipment so that you don't end up draining the batteries out. And the next part is just a kind of an indication of when you should recharge your batteries if they are in storage. Basically, rule of thumb, 4 to 6 weeks. For flooded batteries, VRLA batteries can be a little bit longer. We'll talk about that in just a moment. And there's, kind of gives you a feeling in voltage of when you should charge up your 6, 8, 12, and then you can calculate that on out again for 24, 48 volt systems. And again, when you take them out of storage, charge them immediately or as soon as you can. You do not want to let them sit in a less than charged state any longer, and you certainly don't want to use them when their capacity might be retarded from sitting for a while without being charged. This is a very busy type of chart here, but what you really want to look at is that temperature causes the batteries to discharge even when there's nothing hooked up to them. So in the green line, you see 42 degrees Fahrenheit, and you can be stored out till 16, 18 weeks. If I'm at 85 degrees Fahrenheit, I need to charge those in less than 5 weeks. So that's something that you really want to keep in mind, is staying on top of what the temperature is and how often you need to recharge the batteries. You'll see the same thing on the AGMs, except if you look across the bottom, you'll see storage time in months as opposed to storage time in weeks. AGMs have a much lower control resistance, so they can last longer, but they fall, because they're lead acid, just like flooded batteries, they follow the same temperature action on the self-discharge. Another very important part of maintenance of the batteries is making sure they're watered. Deep cycle batteries have to be watered periodically. Question often comes up, how frequently should I put water in my batteries? And really that comes down to the application. What you want to do is check every couple of weeks at first and see when do you need to put water in. And then you can kind of come back, okay, I went 30 days. I'm going to come back in 30 days again and see if I need to water. I went 45 days. I'm going to come back in 45 more days and see if I need to be watering, because not every application is the same and not every use is the same, but you want to keep on top of that. You want to fill the batteries up to the markings here that you can see. Again, this is on our website to give you ideas. About 1/8 of an inch below the vent well. We'll show you the level that you want to have for the water, for the electrolyte. I'm not going to go real deep into the charge profile, just kind of go over this real quick. There's basically 3 phases for the flooded. There's what's called bulk, phase 2 is absorption, and phase 3 is finishing charge. These are sometimes called different names by different battery companies or different controller manufacturers. But basically, they're the phases where you're charging at a constant current while the voltage comes up. Remember, we're charging the battery, the voltage comes up, and it reaches a certain point, and then the voltage is held, and the current comes down. And what that does is that gets about 90% of the charge into the battery. And then after that, you do this finish phase where you're actually putting the rest of the current, rest of the energy back into the battery. For AGMs, it's a similar type of thing, except there's only really 2 phases. You bring the voltage up to a set point, and then you just hold that voltage there. Some places may call this a constant voltage charge, but you've got again, about 80% comes in until that voltage set point is hit, and then you just want to keep that charge on to get it fully charged. So flooded batteries, equalization. You want to equalize flooded batteries every 28, 30, 31, 32, somewhere around that cycles. What is equalization? Equalization is a programmed or manual but planned overcharge that makes sure to keep putting current into the battery, let the voltage go up, and what you're doing there is trying to make sure that if I've undercharged my batteries during the last 30 days, or if I've got a little imbalance between my batteries that are in my system, if I take this equalization and I go to a higher voltage and I let it run for 2-3 hours or so, then I'm purposely putting a little extra energy back in the batteries to get them equalized. It also will cause gassing inside the battery, and it causes them to bubble. If you ever take the top off and you'll see the bubbles coming up, that mixes that acid so that you get good uniform electrolyte throughout the cell. Another very important part is making sure that the voltage is temperature compensated, and the formula below there, again, it's on our website and it's on our data sheets and it's in our user's guide, and you can use that to make sure that you get the correct set points for your charge controller, depending on the temperature that the batteries are going to be. Same thing with your AGM gel batteries. You've got to have the charge. You do not ever want to equalize a AGM or gel battery. There's no reason to go in there and take them to high voltage. All you're going to do there is dry them out, and you don't want to dry out the AGM batteries. And again, the rest of this, you can find, like I say, on our website for using for your temperature compensation. But do not do not equalize your AGM gel batteries. Charging facts, again, overcharge for stratification should be charged after every use to ensure they're never stored in a discharge condition. A question that we don't hardly get anymore, but lead-acid batteries do not have a memory effect, so you can fully discharge them, partial discharge, it doesn't matter, and equalization. The effects of over and undercharging. Undercharging is about the worst thing you can do, and you can see from there that if you continually undercharge, your batteries are going to continue to underperform and underperform because they're not getting charged back up. If you over discharge, you won't know it for a while because things are going to run along just fine. And then if you severely overcharge the batteries, you will get a rapid decline in the capacity of the batteries, and they'll die quickly. So that's why charging is so important, and proper charging for your batteries. Different battery chemistries. You have a flooded, a gel, and an AGM, and I've spoken to this a little bit. The flooded cell has a separator between each plate, as does the gel, but the gel has the acid, and that's that white stuff that you can see on top. That's that acid that's been mixed with silica. And then the AGM battery on the right-hand side, that white material going around the orange plates, is the sponge that holds the acid. A little bit in the design comparisons, you know, lead calcium, lead antimony difference, the different makeup of the gel, of the electrolyte, and that the gel and AGM have pressure valves. That's why you don't open them up, but the flooded has vent caps that you have to open up to put water in. VRLA battery just means that the gases stay inside the battery and they recombine, and what that does is it keeps the liquid from drying out, and it also means that you're not giving off hydrogen or oxygen during your charging. Batteries never need watering, don't ever water them, and if you do overcharge them, that vent that we talked about, that pressure vent, will open up and let the oxygen and the hydrogen out. Different applications for renewable energy. We have a premium line that, again, this information can be found on our website. We talk about the different ratings at the 5-hour rate, the 10-hour rate, give you some dimensions, give you the weight of the batteries. If you click on each individual one, you can get a data sheet for each individual one that give you a little bit more detail. But this is our premium line product and specifications. Primary battery types. This is by no means a full list, but this is the battery types that you would find that's in use in some of these grid-tied backup. I'm not going to go through everything here except down in the challenges. Getting inverter parameters set to the correct settings is very important. There's different manufacturers that use different terminology, so you want to make sure that you're using the right terms whenever you're setting yours. Depth of discharge, how much capacity do I take out of the battery? If I'm taking 70 or 80% out each time, that will reduce the cycle life. The battery won't last as long. So what you want to do is look at your system and how much you need for capacity. We suggest that you don't go below 50% depth of discharge, so you'll probably want to have twice the capacity that you have need for, and that way you're not over discharging your batteries. Maintenance of batteries, watering sometimes doesn't get performed as required. It's very important. Like I say, you want to check every couple of weeks to begin with and make sure that you, in your application, know about how much water you're going to use. And if you're at high temperatures, that high temperature will reduce the life of the batteries as well, and it will also increase how much water is used. some off-grid applications that use batteries, and we don't need to go through all of these, but microgrids and street lighting and some recreational is becoming much more important, much more popular, and oil and gas, which is a different group. And here are just some pictures of batteries and applications. So there's an emergency backup on the left-hand side, that rural electrification in some other countries, a big, huge solar microgrid on an island. I believe that's just off the coast of Massachusetts. And they're using that microgrid for all the power on that island. Some other applications, street lighting that we talked about, cabin, tiny house. If you go out there for a vacation or spend a weekend or whatever. RVs, more and more putting a little solar or wind or both. And then oil and gas, because they're so remote that no one wants to go out and have to take care of the batteries, so they put solar and wind on those. Lead-acid batteries are about 97% recycled, so that's by far the most recycled material in the world. And as a battery manufacturer, we participate in battery recycling, so you don't have to worry about your batteries ending up in a landfill or something like that. You trade them in, and they're taken, broken down, plastics reused, lead's reused, the material on the plates is reused, the acid is captured, so it's all recycled. If you were to have questions about your Trojan batteries, you can call technical support or send an email through our website, and there's also assistance in sizing for your batteries at batterysizingcalculator.com. So again, if you're wanting to make sure that you get the right batteries for your application, you can go to that website and you can put in different numbers, you know, hey, we've got this, but we're not going to use this or whatever, and you can do it 2 or 3 times and find out what the differences are in which batteries are used. So, best possible solution for long service life is to design your energy storage system to control charging and discharging, and that can be achieved with the proper parameters. Make sure that you're using the right parameters for the batteries you're being used, and you can get that from your superior inverter and controller. So with all of that being said, I'd like to hand this back off over to Doug.
Okay, great. Hey, this is Mark and Doug. Terrific, Tom. Thanks very much. And what we're going to do now is, Doug, if you want to go ahead and make yourself the presenter. And while you're doing that, I do have I'm going to look at some of the questions that came in. I'm going to pose one to Tom. Question that came in is, how often should I check the voltage of my battery bank?
Okay. Well, there's no hard and fast rule in that, but the best thing to do is probably to check it when you go in water. You're right there already. If you have your voltmeter, you can just check. What you want to make sure, though, is to know, hey, have I completed my charging? Am I fully charged, or have I just completed a discharge? So it's important to check the voltage, but also know what where your batteries are in that charge and discharge cycle.
Okay, great. Thanks for the question. Thanks for the answer. And Tom's going to stick around after Doug's portion of the presentation to answer more questions. Doug, before you get started, I just wanted to mention there have been some questions that have come in asking about a recording of this presentation. And for those that joined late, yes, you will be receiving in an email a recording of this presentation. So with that, it looks like, Doug, your slide is showing up here. It looks like you have control, so why don't you go ahead and present.
Okay, thanks a lot, Mark, and thanks, Tom. It's really great to be doing this with Trojan. People can really start to understand better the importance of having the right charge settings for these batteries, and how critical it is to have good, reliable solutions, which Morningstar has been doing for over 20 years. We've been a leading supplier of this solar charge controllers and inverters with the same ownership, management, and distribution partners since the beginning. We pride ourselves on our product quality, and over 3 million Morningstar products have been supplied worldwide since our founding. So this slide displays the controller, in this case the SunSaver, and other components of an off-grid system, and how they're connected to a power to direct current to a DC load, such as the light in this example. When the sun shines on the module, it converts solar into DC electrical power that it delivers to the charge controller. And the charge controller regulates the amperage and voltage that is delivered to the loads, and any excess power is delivered to the battery system that is not used by the loads. And if it's necessary, the battery will also, this is, and what's going into the battery is the net between the solar and the load. So you'll either have flow into the battery or out of the battery, depending on whether the solar is higher than the load. And at nighttime, the solar is disconnected, and you're just using the battery power to get through the nights. Charge controller maintains the battery at its highest state of charge as much as possible while protecting the battery from overcharge by the array. Some controllers include low control for low voltage disconnect to protect the batteries from over discharge. In addition, there are daily on-off lighting control options with many controllers. And charge controllers can also provide system status indicators with meters and LEDs to display battery voltages, current, system operating temperatures, and alerts. Additionally, some controllers include data logging as well as remote monitoring. And on the next slide, we're going to talk about two of the types of the solar controllers that Morningstar manufactures. So we manufacture both PWM and MPPT controllers. PWM controllers tend to be smaller, and they operate at battery voltage, whereas MPPT controllers operate at the maximum power voltage. This maximizes the amount of power being produced, which becomes more significant in colder conditions when the array voltage gets increasingly higher than the battery voltage. So the MPPT controller makes a bigger difference when the array voltage gets high, which means when the modules get cooled, the voltage on the array is much higher, and that's when you're going to get the most boost. There's a good thing in that you need more power in the winter often to make it through the winter. So, in addition, more MPPT controllers can also operate at much higher voltages and lower array currents on the input, which can mean fewer strings in parallel and smaller wire sizes, since there's less voltage drop in with the higher voltage and lower current. This can save a lot of cost in copper, and so that's another advantage of MPPT controllers. And since PWM controllers need to be used with arrays that are matched with the battery voltage, this limits what modules can be used, and the string sizing is dependent on the array sizing will be dependent on the battery voltage. So the type of modules you use, there are a lot of modules such as 60-cell modules with VMP around 30 volts, which many people may be familiar with using with grid-tied systems, which are simply not compatible with PWM controllers at any voltage, pretty much. The advantages of MPPT over PWM controllers come at a cost, however. So it often is possible to achieve a more cost-effective solution with a PWM controller, which will work perfectly fine. And so with smaller systems, it may not pay off to use an MPPT controller. And in warm climates where the MPPT boost is not as significant, it also may make sense to use a PWM in some situations. So each controller has a means to change the battery charging settings. Here we have the ProStar MPPT, which includes 3 ways to change battery charge settings with the dip switches that are right here on the controller, and then with the meter interface. This is our first controller with the meter interface. We're going to have more controllers coming with this meter interface that you can change charging settings with, and then with our MSView software with the computer. So first we have the dip switches. You'll need a pencil or small flathead screwdriver to adjust these dip switches. The main thing is you don't want to press too hard and damage the dip switches, as they're made of plastic. But they work very well. They're easy to adjust. There are 7 factory presets, and the last setting with switches 4, 5, and 6 up, right here, is the custom settings option. So as you can see, it starts with lower voltages for gel and sealed batteries, and then works its way up to higher and higher voltages to the flooded, and the highest is the L16 settings with the highest voltage settings. It also shows the absorption and equalize time here, which is good to be aware of. And I also wanted to mention that you can disable the automatic equalization with dip switch 7 down. So this is really important. As Tom mentioned, you never want to equalize a sealed or AGM or gel battery. So you can still use these settings here in like 1 through 4. I think number 4 is the AGM setting for the Trojan batteries, and you can use that setting. Just you want to be aware that you want to have dip switch 7 down, so you can use this 4th setting with the AGM batteries. And that's really critical that you're not equalizing those batteries with these settings. And I believe this 7th setting here is compatible with Trojan's flooded batteries. I think that's, we reviewed that earlier with Tom. But you can always feel that you want to change any of these settings, and by all means the custom settings are an option, and once you custom program it, this 8th dip switch setting is like an additional preset for your customers. If you want to program it in the shop or something, you can do that before you sell the batteries and pass it on, these custom settings to your customer as a plug-and-play solution. So if you have a ProStar MPPT controller, you have the option of buying it with a meter. And with this meter option, you're able to adjust the custom settings screens for the absorption and low, and here we're showing the absorption and the low voltage disconnect custom settings for the meter adjustments to the custom settings. And this includes many other custom settings adjustments that you can do with the meter. So we also provide a free Windows-based software that you can download from our website. And here you can see the ProStar Setup Wizard, which allows you to make changes to charge settings as well as communications settings and other crucial system parameters. It shows right here the set point summary And here's the setup, one of the setup screens that you go through, several of these screens to create your custom settings. And here again, it's really critical that you get these settings right. You know, it's easy. I mean, if you're not comfortable with your settings, you can probably work with a solar PV expert or a battery expert that can help you with these settings, as you really don't want to create any issues with the batteries that can, if you have set anything too high, for example, it's going to you know, do damage to the batteries. Or if you set it too low, that's also not good, as low settings would not fully charge your battery, and then you're going to have a shorter life for your battery. So all the set point parameters can be programmed using the setup wizard in MSView. The program settings can be saved to a file, and once programmed, the settings are fixed until reprogrammed or with a factory reset. Settings are programmed with 12-volt nominal voltages and will get multiplied by the higher voltages. Here you can see the 12-volt settings that you program it with, but if you connect it to a 24-volt battery, or you have it, the dip switch is set for 24 volts, there's auto detection for the battery voltage, but there's also, we usually recommend setting the dip switches for the battery voltage that you're going to be using. And if you have it connected to 24, you programmed in 12 volts, but it will show up with these 24-volt settings. So you can review all the different voltages that are available for every controller. If I had a TriStar MPPT, for example, it would also show the 48-volt column here with all the settings for that. Here's a quick shot of the custom LVD setting, which can also be used if you want to limit the max depth of discharge for the battery. In this example, the 12.1 volt setting can limit the maximum discharge to about 50%, which might be recommended if keeping the loads on is less critical than preserving the life of the battery. Our default settings are, here you can see the factory default is 11.5. These are going to bring the battery down to maybe a 20 or 25% state of charge. So, which if you're continuously running at that low is going to shorten the life of the battery compared to a 50% depth of discharge. So the idea here is why run the battery if you don't need if you don't need to, if you don't need to run that load, if it's not that critical, why run it down if you don't need to, and you want to have a longer life of your battery. The low voltage reconnect is also needs to be programmed when you're changing the low voltage disconnect, and it is typically at least 1 volt higher than the 12-volt settings. If it is not set, if it's set lower than that, it is possible that the battery voltage comes back up when the load is disconnected. This is because the load pulls down the battery voltage, and then this way the controller will get recharged to some extent before you start running the load again, and you don't have a on-off low voltage disconnect situation. So let's move on to lighting control. Here we have the Sunlight, which is a PWM controller right here, and it's specifically designed for lighting control. And then our SunSaver MPPT controller features lighting control options. The Sunlight is a simple solution with 9 preset options, and the SunSaver MPPT allows you to custom program lighting control with any settings that you want, basically. The ProStar MPPT and TriStar PWM can be used for lighting control as well. They have to be custom. They have custom settings also, same as the similar to the SunSaver MPPT. So here we have a lighting control example of a bus stop using the sunlight. You need a small screwdriver to turn the rotary switch here. Here it is pointing up and going pointing up, so it's pointing to off right now. So you can, this setting's for off, but these other 9 settings are presets, and going around clockwise to the right. This will turn the lights on at dusk, and it will stay on for 2 to 10 hours, depending where you set it, before shutting off the remainder for the remainder of the night and through the next day. And every day we'll go through this lighting control. And these settings here on the left with 2 numbers includes dusk lighting and before dawn lighting. So it'll come on at dusk and then also turn on before dawn, and these are the timings for that. So the controller includes a 24-hour timer, which keeps track of the dawn time, what time the sun comes up, and this is based on the input voltage, or this when the charger starts. When the controller starts charging the battery, that's when it says, okay, it's dawn, it's time to shut off the lights. And so it also will turn it on based on that timing for the next day. So this is really great for bus stops. People arrive at the bus stop early on their way to work. It's dark outside, and so it's a great feature for this kind of situation. Now here's the setup screens for lighting with the SunSaver MPPT. Each screen programs an on-off timer or channel. So each one of these screens programs one of these on-off timers here. On the left, we have the morning timer. One of the good things about the custom settings with the SunSaver MPPT is the reference to solar midnight. By having a reference to solar midnight, the settings will be more stable than a reference to dusk or dawn alone, which you have with the sunlight controller. So the morning is set to come to almost 4 hours after, it's set to come on almost 4 hours after midnight, and the evening is set to shut off at like 1 hour before midnight. So this slider here, right here, allows you to change from a short day to a long day. And on the left it shows a longer day with the summer, and the shorter days in the winter. And this is gives you lets you preview how these lighting control settings will be timed for different seasons. So let's take a look at some of our monitoring features now. Here's a screenshot of the live view web page for the ProStar MPPT, which you can see on a local area network or over the internet. There is a live view web page for each product that has data interface. For the ProStar MPPT, it includes the array information, battery, and load information. It also includes today's charging and load information, which is actually below here, that you can see the amp hours for the day and that kind of information. Depending on the product, you may need our EMC1 Ethernet adapter to be able to see this page with our products. So Live View also includes a data log tab. When you click on this tab, you can see the daily values that are logged internally to the controller. The minimum and maximum battery voltage, along with the absorption, float, and equalize times down here. That's the number of minutes is spent in absorption, number of minutes it spends in float. That information is really useful, so you can see how often the battery is getting fully charged. This can give you a heads up if the battery is going too long without getting to a full state of charge. The log data can help also resolve support cases, and you can identify faults and alarms when you hover over them. So if this was a live screen, you'd be able to hover over these alarms here and see what they are, and it identifies which alarms happened on that day. It can also tell you when your battery is close to the low voltage disconnect, which could also be a concern if you feel like your system loads are very critical, and you can, if that's happening too often, you can see that with this monitoring here by just looking at the minimum battery voltage and seeing how close it's getting to low voltage disconnect. If you want more detailed monitoring and data logging information, you can use MS View. This is the live state view. So we open up here in the displays the live state view here, with this view you can pull any of the variables. Here we pulled them all, but you can pull any one of these variables, and from separate controllers too. You can, if you have a system where there's multiple controllers, you can pull these variables from multiple controllers at once to view them all at once with the state view in MS View. So this allows you to monitor the system in real time, but it's also possible to create a data log file or create a custom data logging for any of the variables in the system, sliding them over into a screen like this for data logging, and then then you can track all these variables over time, and then view the log data in Excel after you're finished logging the data. This is really useful in seeing what's happening when you want to dig down into your system, and you might want to see if there's if everything's going well with your system. Here you can also download the internally logged values, which we looked at in MS View, but you can download that to an Excel CSV file, which you can download and view in Excel also. So here's a screenshot of the daily logged range of battery voltage, which is included with the ProStar MPPT meter display. You can also view daily log values digitally with our meters as well. It is also possible to custom program equipment remotely. This can help improve performance in response to system monitoring, and is also useful if system adjustments are necessary. All Morningstar controllers have a 5-year warranty unless otherwise specified. We are supported by select wholesale distributors, most of which carry Trojan batteries as well. Also, our controllers are manufactured in a certified ISO 9001 facility and subjected to strict quality control guidelines. Morningstar controllers are passively cooled and have no fans or moving parts that can be a point of failure, and also keeps dust away from the circuit boards. Our controllers perform well through a wide range of temperatures, from well below freezing to well above room temperatures, and they have lighting and transient surge protection. Morningstar is easy to integrate with all types of solar modules, batteries, inverters, and other balance of system components. With factory presets or saved custom settings, our customers often say you can set it and forget it. Environmental protections associated with Morningstar controllers include epoxy encapsulation on the top, shown with the SunSaver, and conformal coating with the ProStar of the circuit boards. So I just want to run through one quick example of a system sizing. We're looking at an outdoor lighting in Long Island, New York, with 2 LED lights. And then this would be totaling 20 watts of load when the lights are on. And the load usage would be 4 hours in the evening and 2 hours in the morning. So first we're looking at battery sizing. I pulled up the Trojan battery sizing program and plugged in for 12 volts. Selected a conservative 30% depth of discharge, VRLA maintenance-free batteries, and 5 days of autonomy. So here I also added the quantity of lights, 2 10-watt lights for 6 hours a day, 120 watt hours. The total consumed battery with 5 days of autonomy would be 600 watt hours, which resulted in these 2 batteries. I selected this 6-volt gel 189 amp hour battery. So this is just it's a quick array sizing example using a 120 watt module. The PWM controllers sizing is calculated with array current. So here we're using this array current to calculate the daily amp hours of charging that you would get. And if we had an MPPT controller, this can be calculated using power or watts instead of current or amps in this case, or adjusting for amp hours if you want to calculate it that way, but it's using the power instead of sizing it to the current. This is not meant to be a complete system sizing analysis, but an example only, which I would recommend verifying with an off-grid solar expert. And we generally, however, generally it seems like it will be enough to generate, this size of the system will generate enough energy production, which is about 191% here of the daily load before losses. So during the most critical month, this was calculated for the most critical month of December at this site, given the tilt. So for this size of a module, we're calculating the maximum current into the battery. Since we only have one module, we use the NEC current to get 9 amps maximum current. This is a calculation for the National Electric Code. Our controllers also will protect against overcurrents, but it's good to keep that max current below the rating of the controller. We would recommend always never design a system where the system could operate above the current rating especially for PWM controllers. You would never want to exceed the current rating of the controller. It's a 12-volt monominal module, so a Sunlight SL10 fits the bill, and we would have the settings set for the 4 hours in the evening and 2 hours in the morning. You can also verify string sizing with our online string calculator if you want to, and that's available with many modules, and we update that regularly with modules available on the market. So in summary of this application for outdoor lighting in Long Island, we have this load usage, the settings with the SunSaver, Sunlight SL10. We're using the Trojan 6-volt gel 189 amp hour batteries with 120 watt 12 volt nominal module. And I think I'll turn it back over to you now, Mark.
Sure. Thanks, Doug. Appreciate it. We're going to get to the questions just in a second. We'll just wrap up with a summary. So we want everyone to know that good battery maintenance requires proper set points to be programmed in the controller and or inverter for the battery bank that is being used. It's important to choose the right battery and charge controller for your specific application. Verifying system sizing and circuit requirements with an off-grid solar expert is recommended. And then lastly, Trojan and Morningstar have enjoyed a long-term successful relationship, sharing combined support for numerous off-grid applications throughout the world. So with that, why don't we go ahead, and if you want to advance the slide for the Q&A, and you can show the websites of each of our companies that have been presenting here today. And first question is actually a battery question. Question is, why are VRLA batteries used in Africa? So that question is for Tom.
Well, basically it's because they're less maintenance, so it's easier to put them in place and then not have to be concerned with making sure to go out and put the water in them every couple of weeks. So it's the same reason that oil and gas tends to be mostly VRLA as well, because remote areas, hard to have service people or someone to make sure to take care of watering the batteries.
Okay, very good. I have a question here for Doug about charge controllers. The question is, are the loads DC or AC to the powered Sunlight controller?
That's an excellent question. Our controllers include DC disconnects. So these would be DC loads, and you also want to be careful not to use it with certain types of loads that have surges or very high in surges like pumps. You want to be careful not to exceed the current rating of the low voltage disconnect, as it can damage the circuit as well as if you overloaded the input. So many inverters would damage. Like, we recommend never using the LVD settings unless you're using it with a relay. Somehow we have a diagram on our website that shows how to do this with an inverter. But generally, you would never use a low voltage disconnect except with DC loads that will not exceed the load rating of the low voltage, the load control circuit. And
okay.
Also, inverters generally include low voltage disconnect, and many of them have customs. You can program that to adjust that setting as well with certain inverters.
Very good. Thanks for the question. Thanks for the answer. We have another battery question for Tom. Question is, when would you use gel batteries instead of others?
Well, the gel and the AGM, are going to be the maintenance-free, so that if you are concerned with making sure that you're taking care of the batteries, you would go with the VRLA. Gel, typically, you're going to do better than AGM in a higher temperature. So there is some crossover between gel and AGM, as they're both, valve regulated. But your gel is typically, if you're using something with a little higher temperature, consistently higher temperature, you'd go with gel.
Okay, very good. Appreciate that. I think we have time for one more question. We're kind of up against the clock here, but let's just take one more. This question I'll pose to Doug first, and Tom, if you want to chime in, feel free as well. The question is, what is the default low voltage reconnect disconnect?
Generally, it's 1.1 volt higher than the LVD. So if it's 11.5, I think it's 12.6, if I recall correctly, with our controllers that have low voltage disconnect. But I think there are different default low voltage disconnect and reconnect settings for each controller. So you want to check with it in the manual what those settings are.
Okay, very good. Anything you would like to add to that, Tom, at all, or?
Not about the reconnected, just making sure that you have that low volt disconnect on there so that you don't, over discharge the batteries. But what the reconnect would be, I think, is better answered by what Doug had to say.
Okay, terrific. All right, with that, Doug, why don't you go ahead and go to the very last slide, which is the thank you slide, which also, again, has our contact info, and we wish to thank everyone for joining this webinar, and we will see you next time. This concludes the broadcast.